You know, the microchip is pretty much the heart of modern life, right? But what you probably don't know is that inside every single one, there's a tiny battle happening at the atomic level. And it's a battle that's won by millions of invisible protectors. Today, we're going to peel back the layers of silicon and find them. Seriously, just think about it for a second. What is it that keeps your phone, your computer, all of our electronics from just failing? Well, it turns out the answer involves millions of microscopic ninjas, silent protectors that have been hiding in plain sight for decades. All right, so to understand our heroes, we first have to meet the villain of the story. And in the world of multi-billion-dollar chip manufacturing, the enemy is, well, it's almost impossibly small. That's right, we're talking about atoms. Specifically, stray metal atoms, think iron or copper, that can sneak into the super pure silicon during production. If even one of these little guys is left running around, it can create a tiny, illegal electrical path, a short circuit, that can instantly kill a chip that costs millions to make. And this really shows you what's at stake here. On the left, you've got a perfect chip. Electricity flows exactly where it's supposed to, like cars on a brand new highway. But on the right, those rogue metal atoms create random off-ramps and cause massive pileups. It's total chaos. For our tech to work, keeping that silicon clean isn't just a nice to have, it is an absolute must. So how in the world do you fight an enemy you can't even see? For years, chipmakers have used this really clever self-cleaning trick that's built right into the silicon itself. It's a process called internal gettering, and the idea is just brilliant. You basically create these tiny, intentional imperfections using oxygen deep inside the silicon wafer. These little spots act like sticky traps, so when those rogue metal atoms come wandering by, they get stuck to the traps, way down in the bulk of the chip, far away from all the important circuits up on the surface. But here's the thing that drove the industry crazy. This process was flaky. You know, one batch of wafers would come out perfectly clean, but the next batch, made under what looked like the exact same conditions, would fail. The traps were there, but they just weren't always working. And for the longest time, nobody knew why. This whole mess kicked off a huge scientific detective story. The biggest clue? These traps, these defects, they seem to have a mind of their own, just appearing and disappearing like magic.
And the investigation quickly focused in on one single critical number.
10 million. That's the magic number. Research showed that to reliably clean a chip, you need at least 10 million of these active oxygen traps per cubic centimeter. If you have less than that, the whole thing just doesn't work. So the entire mystery boiled down to this one question. How do you make sure you hit that magic number every single time? And this is where it got really weird. When scientists looked at the silicon early in the manufacturing process, they could barely find any traps. The count was practically zero. But then, if they just waited a little while longer and looked again, boom! The number would just explode, way past the 10 million they needed. It was bizarre. I mean, that was the billion-dollar question, right? It wasn't a slow and steady increase. It was like someone just flipped a switch. The traps weren't growing, they were just appearing out of nowhere. So where were they hiding? And this is where we get the big breakthrough, all thanks to a new theory from researchers Falster and Voronkov. They suggested that the traps weren't coming from nowhere. They were just in disguise the whole time. This line from their paper really says it all. See, everyone else was focused on the traps growing to a certain size, but Falster and Voronkov realized the secret wasn't about size at all. It was about a change in shape, what they called a morphological transformation. They actually called this initial state a ninja particle. And why a ninja? Because it's stealthy. It's a cluster of oxygen atoms that's just hanging out in this relaxed, unstrained form. And in that state, it doesn't create the kind of stress in the silicon that all the standard detection methods are looking for. So it's there, it's growing, but it's completely invisible. It's a ninja, hiding in the shadows. So the whole process is really a transformation. First, you have the invisible ninja particle, unstrained and inactive. Then, once it gets big enough, it undergoes that super fast morphological change. Its whole internal structure just flips. And that turns it into a strained, visible platelet, which is the active trap everyone was trying to find. The ninjas were there all along, just waiting for the right moment to reveal themselves. Now, this discovery wasn't just about solving a cool science puzzle. It was about gaining control. Because if you know how the ninjas transform, you can start telling them when to transform. Suddenly, what was a total game of chance became predictable science. Chip makers could finally stop crossing their fingers and start actually engineering the perfect recipe for cleaning, every single time.
So what's in that recipe? Well, you basically have three main control levers. If you want the transformation to happen faster, you can crank up the initial oxygen concentration, or you can increase the number of spots where the ninjas can form. And temperature? That's kind of the Goldilocks factor. There's a sweet spot. Too hot or too cold and things slow down. But if you get it just right, that transformation can happen incredibly fast.
And the impact of having this control is just massive. We're talking about predictable, reliable cleaning, which means higher quality and way fewer failed chips. This is a huge reason why the phone in your pocket is so dependable. It also saves a ton of time. By really optimizing these factors, you can get this whole cleaning process done in under 10 minutes. In a fast-paced factory, that is a complete game changer. So in the end, this was so much more than just an academic puzzle. By solving the case of the vanishing ninjas, scientists and engineers turned a frustrating mystery into a precision tool, a tool that helps build the powerful, reliable electronics that, let's be honest, we all depend on every single day. Kind of makes you wonder, doesn't it? As you're looking at your screen right now, what other invisible atomic-level transformations are happening inside, silently making our world work?